As Ludo said, I'm an accelerator physicist, so my career has sort of moved between different areas of particle accelerator physics. Actually I started out in this area of medical accelerators, and then when I moved back to Melbourne starting in 2019, I shifted my focus back towards it, partly because I felt that there were many things we could have done and no one was driving them forward and innovating in the space where I could see some fairly obvious bottlenecks in where things were being used clinically. And I'll get to that sort of passion project that I came back to after, sort of 15 years after my PhD in the second half of the talk. But the first half of the talk, I'm really going to motivate sort of why and how we're working in this field, and also tell you about a pretty exciting new laboratory that we've built called the X Lab. So before I get going with the content, I'd just like to recognise that I normally live and work and do my experiments on the unceded lands of the Wurundjeri people, and I believe here we're on the lands of the Bunurong people of the Kulin Nation. So just like to acknowledge their incredible contributions to science, sustainability, and everything else that we do and talk about in our labs. Okay, so the thinking around a lot of the work that I do, both in my science communication work and in my research, really comes from this idea of asking where do breakthrough technologies and innovations come from? And my argument often is that it's not actually the places you think of, like often Silicon Valley, the Apples and Googles of this world. It starts a long way before that. And my argument is that it starts with curiosity-driven research. And I think our field in particle physics, when I say our, sorry, I know I'm talking to a wider department, so who are particle physicists or people that might work with accelerators in the room? Quite a few, great. Other areas of physics or engineering? Do you want to shout out what do you do? Yeah. Electron microscopy, it's basically a particle accelerator. Yeah. Anyone else who wasn't a particle physicist want to say what they do? Nope. Yep. Condensed matter, great. Okay, particles in stuff, that's how I describe that. Not just, I realise. Okay, but that's sort of curiosity driven as well, and translates through to the applied landscape. And I love this quote from the former CEO of the research council that's responsible for particle physics and astronomy in the UK, John Walmsley, who's a lovely fellow, who says that particle physics is unreasonable. It makes unreasonable demands on technology. And when those technologies, inventions and innovations happen, they spread out into the economy and they generate a huge impact. And there have been many economic studies now showing that, for example, for every dollar put into CERN, roughly $8 actually ends up back in the economy. That is an incredible investment if you look at it in that sense. But in our field, based on our fundamental desire to understand the world on a basic level, we've had to invent technologies in order to do that. And one of those key technologies is particle accelerators. So starting back in the late 1920s, early 1930s, with the desire to split the nucleus of the atom, we've seen generations of technology, and this is where the accelerator innovation comes in, generations of technology to reach higher and higher equivalent center of mass energy. This is here, sort of a equivalent energy if you were to put them all on the same scale. And you can see here that there's been many generations of different types of particles accelerators based on different types of technologies that have then come into use around the world in many different ways. And we still use these different technologies because they're good in different areas of society. So for example, down in that lower energy range, we can treat water, food, materials treatment, sterilization, raise the energy a little bit, you're looking at things like radiotherapy in hospitals, security applications like cargo scanning, raise the energy and move to heavier particles like protons or carbon ions. We're looking at proton therapy, which I'll get to later. Higher energy in scientific facilities, we find applications in development of vaccines, in archaeology and cultural heritage. And we're always heading, of course, in generations upwards in energy and intensity now towards understanding ideas in particle physics. So this is an enormous legacy that the field of particle physics and accelerators has sort of given us. And in fact, Alex Chow looked at how many Nobel Prizes in physics are attributable to developments in accelerator science, and it's roughly 1 every 3 years since 1938, or 28% of all Nobel Prizes in physics are actually attributable to developments in accelerator science. And not all of them have been in particle physics, of course. But then I guess what got me really excited when I sort of left particle physics and moved into the accelerator world was the understanding that innovations from one can spill over into the other and make a huge impact. And so now there are about 50,000 accelerators in the world, and about half of them are used in industrial applications, and ask me all about what those are later, but a very common one is ion implantation in semiconductors. All the devices we have that have semiconductor devices in them are now made using particle accelerator facilities. Radiotherapy and medical applications is another huge application, and there's many, many others which I could literally be here all day talking to you about. So when I moved back to Melbourne in 2019, knowing that there wasn't a big accelerator research community here, my job for the last 5 years has been to grow the expertise and grow a team of people who can work together in their different areas of interest to explore the ways in which we can use accelerators for societal good, and particularly in medical applications, and to innovate in accelerators in order to meet those applications. So here's some of the team. It's always changing. At the moment, we have about 10 people in the team. So academic-wise, there's myself, Roger Rasool, and Jeff Taylor, who I'm guessing a bunch of you will probably know those two. The three key postdocs in the group at the moment are Matteo Volpi, Paul Giansiracusa, and Jacinta Yap. That's Matteo, Paul, and Jacinta. And then we have about 4 PhD students at the moment. We've completed 4 already since I moved back here. And at the moment, we have a couple of Labour winter students, undergraduate students as well, but always fluctuating. So lots and lots of activity, and hopefully we'll cover a bunch of their work today. So our focus is really based on computational and experimental work. None of it would happen without national and international collaboration, and I'll talk about a few of those today. We're quite multidisciplinary. So Jacinta, for example, she actually did medical physics in Wollongong, then went to the UK and did an accelerator physics PhD, and then has come back. So she's my key medical physicist. And then otherwise, for those multidisciplinary inputs, we collaborate strongly with people like Peter Mack on some of our more medical aspects. And then we also have some pretty strong industrial connections, because building labs of this scale and with this level of complexity could never happen without actually just direct collaboration with industry. We're often mistaken for the medical physics group. We actually don't have a medical physics group. So people call our group the Medical Accelerator group, which is a little bit confusing. But here's sort of the difference between those two. If you're a medical physicist, you receive clinical training, you work with existing technologies, your focus is really on things like quality assurance, treatment planning, and any sort of innovations in that space. And so from my point of view, that research is focused downstream from the accelerator technology itself. Whereas as accelerator physicists, we're sort of back up in the technology, looking in a broad range of areas of physics, all the way from plasma theory through to electromagnetism, through to superconductivity, all in the one field. We tend to develop novel technologies. That's where we get excited. And we're sort of interested in those upstream or game-changing ideas. So to me, nothing is fixed in any of these technologies, and you'll see that we are really changing or looking to change things quite dramatically. But the interplay between these two is sort of where we come in. So I can't cover absolutely everything that the group does, so I'm going to focus, as I said, on the 2 key areas. One is the X Lab, as we call it, which focuses on compact electron accelerators. And then the second half of the talk will be what I call speeding up and scaling down hadron therapy or proton therapy, which is a new funded project which will be going for at least the next 7 years. So we're just at the start of that one. So the X-Lab stands for the X-Band Laboratory for Accelerators and Beams. What does that mean? X-Band is a frequency. I'll get to why we want that frequency in a minute. It's a very high frequency. And it's been adopted for future technologies in particle physics in particular. SLAC do a lot of work in this space in the US, but CERN have also worked towards developing this technology for about 20 years towards a program called the Compact Linear Collider, which many of you will have heard of, and just generally looking at compact linear accelerator technologies for a Higgs factory type of collider. Interestingly, the collider physics and the medical applications actually have 2 key problems in common. One is compactness. In the medical domain, we want to fit in a radiation-shielded bunker in the basement of a hospital. in this domain, you'd prefer to have a 30-kilometre long machine rather than a 100-kilometre long machine. Quite different scales, but compactness is key to both. And also reliability. In the medical industry, you can't have a machine that sparks and breaks down and fails to deliver the intended dose to the patient. Just like in a collider, if you have 10,000 of these things in a row, if your probability is if one is going to break down, 1 in 10,000 every hour, then your machine is going to break down every hour, and that's no good for doing physics. So solving the technical challenges of how to realise this technology is actually common between the two fields, which is great. So why expand? Why this frequency, which we're working with 12 gigahertz? As you go up in frequency in designing the radio frequency accelerating structures of accelerators, it scales both in the girth or width of the machine and also in the length of the machine. So by increasing the frequency by a factor of about 4 for most commercial accelerators, most are at 3 gigahertz, you get smaller overall dimensions because the radius scales inversely with the frequency. It's also been found when you sustain very, very high electric and magnetic fields in these structures that the higher frequency you're operating at, the higher the sustained electric and magnetic fields can be in those structures. And what that gives you is a higher accelerating gradient. So you can reach a higher energy in a shorter space longitudinally as well. So now we've got shorter or smaller girth and shorter machines. So overall, much more compact, much more lightweight, and much less use of materials like copper, which are quite expensive. So that's one of the key motivations. So this XLab that I keep talking about is actually quite a unique partnership with CERN. It's the first time that CERN have ever packed up part of their R&D laboratory space and actually shipped part of CERN to another country. The fact that we are a non-member state makes it even more remarkable, and it's a collaboration that's been developed over about a decade. So this will make the XLab, or this has made the XLab, the first high-power X-band accelerator lab in the whole Southern Hemisphere, which is a pretty remarkable achievement. And that started well before I joined the university, about 6 years before they started collaborating in that space. So there are many, many partners involved in this, too many to name, but one of the key people who's made this happen at CERN is Walter Wunsch, and the key scientist who's made this happen from the Melbourne side is Matteo Volpi, who now leads this laboratory. So what is the XLab system? Inside it is what we call half of CERN's Xbox 3. They call them the Xbox, forgive the trademark infringement. That's why we called it the XLab instead. So we took half of one of their setups, and what this is it's 2 klystron systems, which are high power 6 megawatt 5 microsecond pulse length klystrons, which are devices that send out very high power electromagnetic waves, basically. Modulators to modulate those waves, and this whole system works at a nominal repetition rate of 400 hertz, which makes it extremely high repetition rate. One of the only other university systems like this is at Tsinghua University in China, and that operates at 50 hertz. So we can operate 8 times faster than one of the only other sort of university-based labs who do this. So this system has a lot of power. By the time we've compressed the pulses from those klystrons down to even shorter pulse lengths, so between 2 and 3 microseconds is the longest we run with, we can get total peak powers up to 50 megawatts. That is enough power, if it's reflected up the line, to melt everything. We have a tower block worth of water cooling in the lab. It has been an enormous renovation to make this system happen. All of that power goes onto this roughly 30 centimetre long particle accelerating structure. And this is where the magic is. This is where the design and precision machining is. And that's the part that your electrons will eventually run through the center of. And the whole rest of it is designed to get power onto that structure to generate the electromagnetic fields that your particles surf along and gain energy through that structure. So just giving a couple of sort of schematics of how some of that happened. At the heart of the project is this klystron device. This was developed back in World War II for the original ones for radar systems, but basically they emit high power electromagnetic waves. I don't have too much time to go into the physics of exactly how that happens, but you have a electron beam in the klystron as well. That's modulated, and then it is bunched in the first resonator. It travels down, and then that bunched electron beam, the electromagnetic field around that, causes a resonation in a second resonator that is then coupled to the output. So you get a small RF signal going in and a very large RF signal coming out the other end. So that power, as I said, it goes into the accelerating structure, which is now, this is a cut through side thing, and then at the end that power is dumped onto a load. Your electrons start here, they travel through the structure, and the electromagnetic wave is obviously oscillating at a frequency of 12 gigahertz in this case. And if you time it right, the electrons gain energy as they go through. And so this 30 centimeter structure can impart about 30 mega electron volts of energy to an electron beam, which is astonishing. We have another accelerator in the basement, which I'll show you later, which is a Pelotron. It's an old school electrostatic machine. That thing can only get up to 3 MeV electrons, and it's 3 stories tall. So that for 30 MeV, even though it's for electrons, is astonishing. And so the gradient here is over 100 megavolts per meter, which is the world leading accelerating gradient. So it's been a long journey. During COVID times, we shipped all the equipment to Melbourne from CERN in a shipping container. We had to get professional riggers in to lower it all down into the basement. And you can see we're still masked up at that point, but we got it all in. The refurbishment has been just as long a journey. The lab has been there since the 1970s. You can see it wasn't really being used as a research lab, more as a storeroom and workshop. So it all got emptied out. It's had a beautiful refurbishment that cost about $1 million to do, upgrades to the radiation shielding, and et cetera, and the equipment has now all been installed and put in, and then it had to get back up and running because you can't just switch everything on. Everything has to be recommissioned to get it back up and running at those incredible high powers, because if you connect anything wrong, if you get a mismatch in impedance, if you get anything like that, you're going to get RF reflection back up the line, and that's disaster. So it's an extremely careful Lego building process. We have a little Lego sign on the wall to remind us of the thousands and thousands of pieces and hundreds of meters of cables and all of these things. So the layout, for those of you who have more of an electrical engineering background, is we have the 2 klystrons and modulators. We have a series of directional couplers, which bring us down to these devices called pulse compressors. They simply compress the pulse in time, which increases the peak power. And then we've got 2 waveguides which head through this radiation shielding wall at the back into our experimental area, which, despite the look of the walls, that's actually underground and under it's under the lawn by Swanston Street, if you know where Melbourne Physics is. That lawn with tables on it where there's a cafe, that earth is part of our radiation shielding. Don't worry, we have tested the radiation levels outside that. And then out the back here is where the structures will sit and be powered by this system. So this was Valentine's Day, February 2023 last year. We had a visitor from CERN who was helping with the commissioning. And so this is just a quick scan around some of the equipment. I'll show you some pictures in a minute. And then can you explain what you just did?
Yeah, I mean, just parts that we have with the plastic tubes, and we have a small amplification. So that means the guys are working properly. Of course, we are speaking about what they call the 300 watts.
So is that the first 12 gigahertz in the southern hemisphere?
Yes.
Yeah.
Yeah.
And then we pop champagne in the lab, as you do. This was last year, was the first high-powered pulses in the southern hemisphere, and now we are commissioned and running up at full power as well. So that was a lovely moment for the team after a number of years bringing this project here. But I know what everyone always wants to ask, so what are you going to do with it? It's a wonderful piece of kit, it's a wonderful lab. What are we going to do with it? We are threshing out the science strategy as we speak, but there are a few focus areas that we're going to start on. the wonderful thing about accelerators is that you can do so many different things with them. The difficult thing about accelerators is focusing on which things you're actually going to do. We have a couple of focus areas, but I do want to recognise that the strategy is really underpinned by people and expertise, skills and collaboration. Without that, none of this would be possible. The equipment is about $7 or $8 million worth. The lab reno was $1 million. We have a team of sort of 5-ish people on site, but then there's probably 20 people that we are regularly in contact with around the world who are inputting to this collaboration. And to realise that in Australia means that collaboration mode is more important than ever. But the first key application areas we're going to focus on, and the ones I'll talk about today are in red, are in the medical, scientific and obviously accelerator science areas. So in the medical, I'll talk about what this is in a moment, very high energy electrons and flash therapy. In the scientific, we have a very close collaboration with your friends over the road at the ANSTO Australian Synchrotron on compact light sources, because you can actually, with these expand accelerators, you can interact a high power laser coming in the other direction and create Compton backscattered photons. And those Compton backscattered photons basically do the same job as the whole Australian synchrotron, but on the scale of our small lab. So people have in other universities around the world developed lab scale light source facilities that are particularly good for biological applications, but that would be a whole separate talk. So we can invite someone back to give that one another day, but we'll be collaborating on that one. There's a whole lot of accelerator science and accelerator physics areas and technology areas that we also want to research, and the one that I'll just highlight today is actually around the science of breakdown, or the science of how those high voltage, high field structures actually go through the process of the materials breaking down under those fields, and how that all works and how we can reduce that so that when they're in operation in a collider or in a hospital, they don't break down all the time. So that's one of the areas of focus. So I'll start there actually. So we're conditioning, our commitment to CERN for the long-term loan of the equipment is to condition, it's called, these what are called TD24 structures. What that means is that there's 24 high precision milled discs in a row. I'll come back to those in a bit. So they're milled to about single micron precision, which is unbelievable. And again, I'll mention that again. And then brazed together into this structure. We add the water cooling, we add everything else on there. But the thing is, you can't just generate one of these. You can't, even if you have single micron precision milling, you can't just build one, put 50 megawatts on it and expect it to work. It's like having the world's toughest leather shoe. You have to break it in, right? And this is where the science of breakdowns and conditioning happens. So our commitment is to use this system to actually condition the structures for the Collider program at CERN, and then we have the capacity to do other ones as well. So when you get this RF breakdown effect, where you have a very strong buildup of charge on the surface imperfection inside the copper, it can cause a number of destructive things. One is that power reflection I talked about. Another one is you get a sudden breakdown, so you get sudden pulses voltage-wise. That can cause a destructive sideways kick to a particle bunch. And if you're in a collider, that absolutely destroys your luminosity. So we don't want that. So this process of conditioning the goal of it is to attain the lowest possible breakdown rate once you're up in normal operating mode at full power. And so over the years, CERN have tested and every structure has to go through this process. They've tested each of these structures up in terms of gradient, so the gradient achieved, the pulse rate, the pulse duration, and they sort of increase these values over time. At the moment, it's a bit of an art rather than a science. So part of our goal is to wrap around a bunch of diagnostics around this, and we're starting to look at using machine learning techniques to make predictive breakdown a possibility. So far, one of the structures that we have here, this is the data from CERN before it came out to us. So that's reached just about 100 megavolts per meter. Some of them have actually exceeded that. So if you go in the lab today, and you're very welcome to come and visit, we'll show you around any time. We love having visitors. It looks like this. We have a very beautiful black floor and black ceiling. It's very space age. And so the parts of the system here, this is the low-level RF, which is just generating the signals. The klystrons, as I said, behind that is the pulse compressors. Looks a bit messier now with all the cables, huh? That comes through the back wall into these two waveguide lines, and that will come down onto the test stands, which we're about to connect up, so I haven't got a photo of that yet. But we are now running in the lab at full power, and before we can put all that power onto those structures, we actually have to recondition all the other things in the line as well. So we have actually been reconditioning the pulse compressor structures, and actually that's been quite interesting because we've been able to observe breakdowns on that, and that's a whole specialised area, but feel free to ask me questions. For the sake of time, I won't go into too much detail. Around this, of course, is a whole development of other lab facilities, things like something called a bead pool system, which is where you send a dielectric bead through the structure to measure its efficiency, effectively, the input and output reflected waves. So we've sort of built up a whole system around this laboratory. So if you need any of those, let me know. So that's the sort of accelerator science studies that we're going to be starting with. The other thing I said I'd mention is the medical ones, and that's enabled by an ARC LEAF grant to build the XLab beamline. So that's to transform the system from a accelerator test facility where we're just testing these structures into an actual electron accelerator. And that will make it basically the only pulsed tunable electron accelerator available in a hands-on way to researchers in Australia. And when we realised that Australia didn't have one like that, we were actually astonished. So this grant is the easiest grant I've ever won, because when you make that argument that we literally don't have an electron accelerator available to people in Australia, it was easy to get. So we're adding to these cavities. We're going to turn the cavities sideways so the beam goes through them, add an electron gun, add a whole bunch of magnets and diagnostic sections and a spectrometer, and a whole lot of other things to actually turn this system into an electron accelerator. In the first instance, that'll be probably up to about 20 to 30 mega electron volt energy using a single cavity, but we can go with the two cavities that we own, we can probably go up to about 40 in a reliable sense. We have the space potentially to go up to 100 or more in future if we procure more cavity structures. So that's underway at the moment, and there are many potential users who are going to come and collaborate with us on that, from biophysics to space plants, ask me more later, development of diagnostics and dosimetry, so we work with University of Wollongong and University of Sydney on those, radiotherapy technology and all sorts. But the one thing that I'm quite curious about, and we have just had our new student whose name is Joel, who has just commenced last week, is this idea called Very High Energy Electrons. Now I'll come back to a similar plot to this later, so it's worth explaining in a bit of detail. So when you put different particle species or different types of radiation, so photons, electrons, protons, carbon, etc., into dose equivalent, so water basically, tissue equivalent into water, they each have different dose deposition curves. So if you put X-rays in, it looks like this. So the dose peaks just under the skin and then falls off with depth, more or less exponentially. The ones I'll show you again later are this orange curve. This is called a spread out Bragg peak, and beneath that there's this pink one here which is called a Bragg peak, and that's what happens when you have protons or carbon ions. You get this peak at some depth. That depth is tunable depending on the starting energy of the beam, so that's great for reaching tumours deep inside the body. But an idea that's only recently sort of come back on the agenda is the idea of using electrons at a higher energy than we currently use clinically, because currently electrons do roughly the same as photons there. They're not very good deep in the body. Oh, actually, sorry, I think D there is actually the electrons of the current energy that we use. But if you use higher energy electrons, say 100 to 200 MeV, and you focus the beam in, you can achieve peaks that look more like this red one here, or even H, the black one there. And that's quite interesting because you're doing away with some more of the entrance dose, And you're also doing away with some of the exit dose that you get with X-rays. The other interesting thing about using these high energy electrons, especially in focus mode, is being able to deliver the dose very, very quickly. There's been some radiobiological findings that are not fully understood yet biologically that say that if you deliver dose much, much more quickly than we currently do, it has the same cell killing effect on cancerous tumours, but the healthy cells are far less damaged. So that actually increases your therapeutic ratio. And that's called the flash effect because you're effectively delivering the radiation in a flash compared to what we do now. And that has the capacity, if the ideal world and it all works out, to reduce the way that we treat cancer patients from someone having to come back in 25, 30 days in a row to receive their fractionated treatment to only having to come in once or twice, getting basically all the dose in 1 or 2 sessions and walking away, which is just completely transformational in terms of the way that we treat cancer, access, capacity, the number of people we can treat, etc. But the exciting thing about the X-band technology that we work on, coming back to that gradient I mentioned, that 100 megavolts per meter, is at the moment, if you took our existing technology and wanted to have a 200 MeV electron beam, which is about where this operates, it would be a 20 meter long machine. And that's really hard to fit in a hospital, especially to retrofit into an existing radiotherapy system. But using this X-band technology that we're working on, that's a meter. So now it starts to look the same as your regular radiotherapy systems. And that's got people pretty excited. But there are so many unknowns. This is still very much in the research phase. We don't know for flash what the pulse structure should look like or exactly how fast or in what order, beam should be delivered. We don't know how stable the beam has to be. None of our dosimetry can cope with dose coming in at this rate. How do you do quality assurance when things happen so quickly? When would you choose high energy electrons compared to protons, compared to regular X-rays? Many, many, many questions. So we're just embarking on starting some research in this area. If it's an area that you're interested in or know someone who's interested in, please come and chat to us. So we'll be building a end of beamline sort of water tank dosimetry station in the first instance. We could think about having small animal studies in vivo and things like that. Just one quick thing to mention that's come out of the XLab project before we were even operating is actually upskilling the ultra-high precision machining capacity in Australia. So I said before that we had up to, or down to, single micron milling. So this is one of the discs that I mentioned before, which was one of those 24 discs all brazed together into the accelerating structure, and the electrons go through the central iris there. Particularly this curved part of the iris obviously has to be very smooth or everything just breaks down. That's where you need the single micron precision. So good milling is about 50 micron, very good milling. Probably a workshop here could do that with a CNC. Really good milling is about 20 micron. But to do this, you need a diamond tip nano milling machine, of which there are only 4 places in the world that can actually mill these discs. And if you walk in the room while it's milling, your body temperature will ruin the tolerance. That's how precise it is. So one of the lovely things that's happened is that the Australian National Fabrication Facility milling centre in South Australia have actually invested in one of these diamond tip nano milling machines. I will admit that it was not just for us. There were other applications in other industries that were also interested, but having our research challenge actually really helped them make the case to invest in that, which is great. And so they've already actually made us roughly a 20 micron precision flange for part of the system, which is in one of our lines. And then the next challenge is for them to actually make one of these discs, which they'll be doing over coming months. So this is pretty exciting. Australia could be, one of only then 5 places in the world that could actually do this. And so they've actually already got requests from labs in Europe asking them to make these components, even though they haven't even demonstrated they can do it yet. That's how rare the capacity is. So that's pretty exciting. So the status of that lab at the moment is we've got this amazing multi-million-dollar equipment from CERN. It's been commissioned at the University of Melbourne. Really, that's our central infrastructure, and then from there we grow in scientific direction. We had our first pulses in 2023. It's taken us a year of rebuilding that, measuring everything very, very carefully, moving up in power to reach the maximum power, the same as it was functioning at CERN, and then we're imminently connecting that onto the accelerating structures, and then we're back in science mode testing the science of breakdown. You're very welcome to visit, and you're also very welcome to come and play and help and support if you find that you have skills that you would like to contribute. Okay, let's check time. Spent too long on that, haven't I? I'm going to have to go quickly through particle therapy, but let's keep going. So the other half of the program, and the one that I really wanted to bring back to Australia when I came back here, is in the space of particle therapy. In Australia, we talk about protons because we're just getting our first proton therapy centre in Adelaide, which is under construction, and the second one is under construction in Brisbane, and they're now somewhat in a neck and neck race of who will treat patients first, which is great. It keeps them driving forward. The facility I'm standing out there with two of my former PhD students is the MedAstron facility in Austria. So that is a synchrotron designed to treat patients with both protons and carbon. You can see the scale of this facility, right? This is not a normal hospital. These facilities are enormous, and that is one of the big challenges. Back to a simplified version of that plot I showed you before. So proton beams at roughly 250 MeV are sufficient energy to go basically as deep in the body as you need, depending on the direction you shoot from. And then if you lower the energy, that peak occurs at shallower and shallower depth. In reality, that's actually too sharp a scalpel to treat with. It's really precise. So they actually spread out this Bragg peak by delivering a range of different energies. And the therapeutic advantage of this, which has now been demonstrated in over 250,000 patients around the world, is that you often get a sparing of critical organs and less dose to healthy tissue than you would have with, this is intensity modulated X-rays over here, protons there and carbon ions there. It's great for hard to reach tumours, it's great for tumours in sensitive areas like in the brain, and it's great when you want to avoid critical organs, say in the abdomen. It's also fantastic for paediatric patients, for children, because any of that unwanted radiation dose would increase the chance of a secondary cancer later in life, which you obviously don't want, especially in young children. So we've been collaborating with CERN on future designs of these systems since about 2019, and we've now grown our collaborations in the US as well. So one area that we're working on is the design of next generation facilities, including very compact superconducting synchrotrons. This one here is 27 meters in circumference, as opposed to about 70 meters of the machine that I showed you before. But I'm just going to skip over a bit of that. We've had some fun with a former PhD student who's now completed doing automated optimization and genetic algorithmic design of synchrotrons and things like that. He's now working at the Australian Synchrotron, designing the next generation Australian synchrotron using his automated lattice design, which is lovely. The thing I want to focus on is actually not the machine, but we could have a whole conversation about that. The thing I want to focus on is the beam delivery. And what we mean there is getting the beam from the accelerator to the patient and where it needs to go. So just to show you a little video, this is from the Bragg Centre in Adelaide. So they've got a synchrotron as well, but it's a very compact one. The beam is accelerated. It's sent down a series of beam lines and bent into this enormous device, which is called a gantry, which has to come up and over the patient and delivers the beam precisely where it's needed. That entire structure can then rotate, either depending on the design and the company, between 180 and 360 degrees all the way around the patient. The patient doesn't see that. They're in a specially designed room, so they actually don't see the enormous infrastructure around them. But these things are hundreds of tons. They're physically enormous. And this is why proton therapy, although it's extremely promising, is very expensive. So one of the collaborations that we've just initiated is funded through the US National Institute of Health with our lead PI. His name is Konrad Nestoruk, who's Harvard Medical School and Mass General Cancer Center. They're one of two other places in the world that actually have the same synchrotron that we're getting in Adelaide, just out of interest. It's also a collaboration with industry, so Pyramid Technical Consultants. They make the final bit of the system called the nozzle, which actually directs the beam and scans the beam across the area where it's required. So they're the three key partners. We're funded, actually, the project was so highly scored that we were funded for 7 years instead of 5. So I'll sort of explain what the plan is. We're just at the beginning of this grant. And the aim, as I said right at the start of the talk, is to scale down and speed up proton therapy. The scaling down, I think you should get the impression already, we want to decrease the size of all the infrastructure. Our aim for this project is to fit everything you need for proton therapy in the same size as a radiotherapy bunker, so you could retrofit proton therapy into somewhere like Peter MacCallum Cancer Centre in Melbourne, who are very interested. It's also doing away with the need for that giant rotating gantry, because there now exist upright treatment chairs where the chair rotates, so you can have a fixed beamline. And that's a relatively new innovation. But the other thing we're doing is speeding it up, and we're aiming for what we call ultra-fast dose delivery. So at the moment, standard dose delivery, or the time it takes to deliver one treatment or fraction to a patient, is about 1 to 5 minutes per field, and there may be multiple fields in a single patient treatment. So your patient could be on a couch or in that chair between 5 minutes and an hour or more, up to the level of patient comfort. They're often immobilized. For children, they have to be under general anesthetic. It can be very uncomfortable and very distressing. So that's what we do at the moment. We just expect patients to deal with that. Fast dose delivery, which has been the focus of the field for about the last 10 years, is about 1 minute per field, and they can do that by cleverly using their treatment planning software usually. We're aiming for ultra fast, or under 10 seconds per field. If possible, we'd like to also stretch down to the very super ultra fast, I don't have a word for it, the flash regime that I described, where you really deliver all the dose very, very quickly. We're going to explore whether or not our technology can do that. So what are the benefits of doing that? Well, it's no longer possible just to sort of treat a patient with a wide field and sort of hope that it helps them. That is very much not modern radiotherapy, and it's very much not modern proton therapy. Inside the body, there are lots of moving targets. If you have a cancer in the lung or in the abdomen, it can move by up to 10 centimeters with the breath movement. So at the moment, we apply motion mitigation techniques like asking someone to hold their breath on a pattern, and then shoot, and then shoot, and then that delays the treatment, right? That's why these treatments can be so long. So one of the things is you can treat moving targets, and you could potentially treat them in real time. So you don't have to do the breath hold, you don't have to do anything else. You can either treat so quickly that the motion is basically non-existent, or you can move with the motion. The other benefit of ultra-fast dose delivery is that overall treatment time. So we're aiming to at least decrease the treatment time by a factor of 2, but our even basic estimates say that we ought to be able to decrease treatment time by a factor of around 10. And the clever trick of how we're doing that is coming. So that can increase the throughput in terms of how many patients you can treat per day, which obviously helps in terms of overall cost and accessibility. It's also much better for patient comfort. These patients are really sick, so staying in a position, immobilized, often with a mask that physically holds your head so you can't move it, it's really, really uncomfortable actually experiencing these treatments. So this is just a little thing which is supposed to show you the problem with moving targets. So the way we treat in proton therapy is called spot scanning. So you have a small spot and you map out and paint the sort of volume of the tumour, and you do it one energy layer or depth layer at a time. And so if you've got this pattern in light grey and you're stepping between the different spots, but your target actually moves, you can see that your treatment plan is not going to be delivered as you would have liked. So when I talk about the treatment delivery, one of the key things that I'll highlight is the way in which we change the energy. So you have to scan position to put the spots in different locations, but you also have to scan from through different energies. And usually we start at maximum energy, and then we change the energy layer, and we scan again, and we change the energy layer, and we scan again. And that's how these treatments are delivered in 3 dimensions. And the time it takes to change this layer is called the energy layer switching time. And it is, as we discovered when we decided to write a review on it in 2021, the bottleneck. It is the bottleneck in the treatment delivery time. In fact, for the majority of tumours, it dominates the delivery time. It's up to 70% to 90% of the time. Your beam is off and you're changing energy. I can go into detail later of what that is. So why is your beam off? Why do you need to change it? Why does it take so long? Because your beam has to go through that beam line that we showed you in the video, either down the corridor or up and over the patient, or in our case, round a corner and into the fixed beam line. All that time, that 70 to 90% of the treatment time, is when you've turned the beam off because you're waiting for the beam current in your magnets to change to the new setting so that you can deliver the new energy. That's it. It's physics. It's if you go faster than that, you get eddy currents, you get hysteresis, you get all sorts, and your magnets settings aren't correct. It's literally, it's a physics limit of why we can't deliver patients faster. So the trick around this is to use what's called a large energy acceptance. So for that, we need some 101 accelerator physics, which is when you send a beam through a series of magnets, which are designed to bend or focus in this middle one here. If you have the nominal energy, it will go through the center of the system. If you have an energy that's too low, it will bend more here, it will be focused differently here and bent back there, and an energy that is too, high will go further outwards. You can somewhat get around this and increase the amount of energies that your beamline can accept by doing a clever thing with some more focusing in these sections here, and we can implement what's called achromatic bending. If you're used to optics and achromats in optics, where everything is, every colour can be transported, similar idea, but here colour is energy. So there's been a push for a number of years around this idea of increasing the energy range of the beam that can go through a single beam line. A normal acceptance is about 1%. Our project aims up to about plus minus 50%, which actually is the entire energy range of proton therapy. This has not been done before. So we've gone through why that's so slow, sorry, so I'll just skip this little bit. So here's where the magic is. In my group, we've used a novel type of particle accelerator optics called fixed field alternating gradient optics, or FFA optics, to increase the acceptance of a beamline from the usual 1%. And if you vary the energy outside that 1%, your beam hits the edge of the beam pipe and is lost, right? We've used nonlinear magnetic fields and optimizers and this optics approach to actually achieve, here it's plus minus 42%, which is equivalent to the full energy range from shallowest to deepest in proton therapy. This work has been done by my PhD student Adam Steinberg, who's shortly about to submit his thesis. And this has been a challenge in the field for at least the 15 years since I finished my PhD in a similar area. I was designing accelerators, he's designing beamlines. So it's taken me 15 years to come back to this problem and work out how to solve it. And thanks to the amazing optimizers we have nowadays, we have actually finally solved it. So not only are these energies transported, and you can see they go at different positions through the beamline, and that's where the magic is. We've actually managed to solve the problem so that the beams can all come in at the same position and angle. They can all come out at the same position and angle, but by following different trajectories through the beamline, they can all go through without having to change the magnetic settings at all. So this means you can go as fast as you want through this system. We've completely technologically removed the bottleneck in proton therapy, in theory. Just to visualize that, if I have beams of different energies, the low energy is on the right and the higher energy in the red is on the left there. This is the beam's eye view through a beamline like that. It looks very unusual compared to a normal beamline on an accelerator, but it means that you can transport all of these different energies without changing anything. If you wanted to, you could transport all of those different energies at the same time, which opens up completely new treatment paradigms, and it's something that we're considering. So it's one thing to solve a thing in a simulation, and it's another to do it in reality. So that's what this 7-year new collaboration and grant is for. There are 3 parts to the project. There's getting the beam to the right energy very rapidly, for which we use a very rapid degrader system, which is just physical material put in the path of the beam that varies the energy. That's being done by our Harvard and MGH colleagues. At the other end, there's that fast scanning nozzle to do the X and Y translation. But in the middle is Melbourne University, and this is why we're partnering on this grant. In the middle is this funky new beamline technology. And so what we're doing as part of this grant is building the first scaled down prototype of this system in the basement at Melbourne Uni on this lower energy up to 3.5 MeV proton accelerator called the Pelletron. So that means we can't use any of these existing beamlines. We're actually building an entirely new beamline off behind this direction here. And all of the studies and beam shaping and everything we've needed for that is what we've been doing for the last couple of years. And now we're in a position where we are ready to build out this prototype, demonstrate the technology, and de-risk it in order to scale up to the full clinical energy in the future. Some of the questions you might ask is, okay, this beamline, I briefly mentioned it uses nonlinear magnetic fields. What does that do to the actual beam itself? The answer is not much. It's pretty round, it's pretty good. A treatment planning software should be able to use this. So that looks okay. We've had to do a lot of integration studies on how you use an old school electrostatic accelerator to feed an experiment like this. It's not obvious. We have a totally different language. So there's been a lot of learning and a lot of understanding how to use diagnostics, slits, collimators, etc. in order to do this. So I'll jump over that, but we have because I want to get to one other thing. So we've had to do a bunch of measurements, install some new diagnostics, measure the phase space of the beam, the energy distribution of the beam, and everything else. So we're confident that this is going to work. One of the interesting innovations that we decided to make is actually in the magnets, of how we're going to make the magnets for this test beam. Because to me, working with a university scale lab, I want a setup, a beamline setup, where I can test multiple different ideas going forward. This is just one. There's lots of other really interesting ways of transporting and manipulating beams that we could test in the future. And one of the issues with accelerator test experiments, first of all, is the cost, right? Magnets are expensive. So one way to get around that, and because we don't have to change the fields in the magnets, is to use permanent magnets. Great. And you can actually, and this is Adam's work again as part of his thesis, we can actually run optimization algorithms, and here we've run one to create these highly nonlinear fields that we need that look a bit like this. And through an optimization process, he's removed the unwanted additional multipoles that we don't want, and he's managed to achieve the field strengths that we do want. But the key thing here is that instead of having custom-made pieces of, say, neodymium or samarium cobalt, which are very expensive to have custom pieces, he's used commercial pieces that you can buy for a few dollars each and designed it so that you can place those into a 3D printed magnet holder. Sorting out the forces is interesting, but we're at a low enough energy that the magnets aren't too strong, so that you can achieve these magnetic fields. And then once your experiment is done, we can simply take the pieces of magnet out, reprint something new that a new student might design, put them all back in, and the whole thing becomes sustainable in terms of the equipment that we're using, which was very important to me because I've seen a lot of very expensive equipment go to waste after a 2-year grant, right? So that's why these magnets now, they look a bit higgledy-piggledy, but they're totally achievable. That is about this big, just for context. So we have started doing some prototypes of these, and it looks like the fields are going to meet the specifications that we require. Because it's only a beamline, a single pass system, the fields don't have to be as precise as like the Australian synchrotron, but they should be good enough. And then we put that optimization back into our simulations and everything looks great. So that's where we're heading with this. We're going to be demonstrating this technology over a number of years. There's obviously lots of challenges involved in the integration of that, in the timing, in making sure that the beams can get in and get out and also be quality assured in a hospital. But thankfully with this new collaboration, we are going to be well on the way to actually using this technology to hopefully speed up proton therapy while also scaling it down. And so we have a lot of interest from centres around the world, but especially from the ones here in Australia, about the potential of Australia actually having world-leading, fastest in the world treatments in proton therapy. That's the goal in about the next I'd say 10 years. For the sake of time, I'll skip over this, but just to say we have re-established a collaboration called the Australian Collaboration for Accelerator Science, which is at the moment between ANU, ANSTO and the University of Melbourne, the three that have the biggest accelerator facilities. But this collaboration is going to be expanding over time to include both other academic partners, so you'd be very welcome to join, and also industry partners to grow the skills base and training and collaboration that we need in Australia to move the field forward. So before I say thank you to you, I have obviously an enormous list of thank yous to all of our collaborators and everyone involved in the many, many projects that we're working on, but particularly to all of our collaborators who are working on the XLab and the so-called Turbo project that I've shown you today. And I'll stop there. Thank you for your attention.
I'm very intrigued about the issue of the conditioning.
Yeah.
That you have. What actually happens during the conditioning? What is it that, what happens physically, and how do you actually cure it to some extent just by using it? Why don't you slowly wear it out? You actually slowly get it better and better.
So even when you precision mill copper, you still have surface defects and things, right? And it's mostly the surface that we care about, but slightly deeper than that as well. So what happens basically is when you put these very high electromagnetic fields, they will concentrate on whichever area has a defect, and that will just slowly, you'll get a higher and higher field around, say imagine it's like a point, right? And then you'll get an electron avalanche. That then has enough power to actually physically melt the copper area, and so that will then sort of iron out that defect and the field will concentrate on the next one. That's sort of my very hand-wavy explanation of how that works. There are all sorts of theories in terms of the build-up of plasmas and things that other people are much more expert on than I am. But one of the things that's very difficult is knowing exactly how quickly you can ramp up the field in terms of pulse length and also pulse height, so power. And as I said, it's mostly been done kind of just with a slow ramp up over time in most of the labs around the world. There was a paper that came out a couple of years ago that seemed to show that you could predict when a breakdown was going to happen based on all sorts of fluctuations, including vacuum fluctuations. But the timescale of the breakdown is actually, well, our group was like, okay, the timescale of the breakdown is far too short for the vacuum fluctuation to be observed before the breakdown. And our master's student who's now doing PhD actually sort of disproved that theory. But that's why now we're sort of looking at, okay, well, what predictors are there, in terms of what we're reading out, which is, we're mostly reading out power, throughput, power reflected. We can observe things on the beam itself as well. And then we also we've installed optical fiber beam loss monitors as well, because you get, because of these effects, but also just because you have a very high voltage on copper, you get dark current as well coming out. And so that the fluctuations and changes in that dark current can also indicate when you're about to have a breakdown. And as you condition, the amount of dark current reduces. So that's sort of how you know that you've got to the point where any of those defects should be now ironed out. But it's a combination of electromagnetism, physical material defects, and the plasma effects that are happening.
Thanks for the fascinating presentation there, Suzie. It's really amazed by the electron beam Bragg peaks that you can produce. Obviously,
yeah, those focused peaks. Yep. Yeah.
I didn't know you could do that with electrons, and obviously people have spent billions of dollars building proton therapy centers all around the world. Why is it that no one's been using electrons before? Because they seem so much better.
So if you look at just the distribution for unfocused beams of electrons, it is almost, it's not very good. Basically, it's a broad curve that sort of just goes through. I think where people started to sit up and pay attention was when someone thought about focusing the beams and what effect that has. But that said, when you focus an electron beam into tissue or into water, of course, there's all the multiple scattering that happens with that, and so it broadens back out. And so the studies that are happening at the moment are around, how well can you actually keep that focus? Do you have to change the energy and the focus, at different depths? How can you actually achieve that? Is the upstream dose going to be a problem, especially at that those high dose rates. I mean, you would think it would be helped because you're wider at the skin surface and you're narrower down, deep inside the body. So those are sort of the physics reasons why it hasn't been used before. The medical reasons are just that we've never had machines in hospitals that are commercial that can reach anywhere near this energy. The highest energy hospital-based radiotherapy systems are 25 MeV, and that so electrons are used in clinic, but they're used for skin lesions and just below the surface of the skin, and not really for anything else. So. Of course, to a physicist, it's obvious that if you have higher energy electrons, they'll go deeper in the body, but it hasn't really been looked at or been looked at as an advantage radiobiologically because protons have that advantage of stopping, and they have the sort of low entry dose, and it wasn't realised until recently about the focused aspect. So watch this space. There are certainly people in commercial industry who are not really believers, I would say, in the very high energy electron therapy. I'm agnostic. I'm just curious as to how it would work and what the problems are and how would we develop an accelerator with sufficient beam stability, reproducibility, etc., that is small enough to actually do it. We may later have a look at the beam delivery because that's obviously become one of our areas of expertise. But yeah, so it's funny sometimes, like, the physics answer can be obvious, but actually translating that into a clinic is decades of work. So, thanks. I've got one PhD student on it, so it will take a while. But
Any other questions? I have a couple. So the first one is very general, but patients who get treated with, say, proton therapy, do they still get chemo and standard radiation therapy as well?
Often, yeah. So about half of all cancer patients are treated with some form of radiotherapy. About 10% of those are indicated for protons if they're available, but they're obviously a lot less available than radiotherapy. A lot of those patients who get radiotherapy have multiple forms of treatment. So they're often prescribed immunotherapy, chemotherapy, and surgery alongside that. But I should say that of the successfully cured cases, and cured here usually means a 10-year period without recurrence, around half of successfully treated cases are treated using radiotherapy, which is a pretty phenomenal track record, and yet only about 5% of research funding into cancer treatment goes into radiotherapy of any sort. So that's my political statement of the day.
I have another. It's probably either stupid or undoable, but so the way you the way you do it is you focus the beam and you scan over the tumor over several energy layers. So if you were targeting only one energy layer, could you imagine having a broader beam but sort of shaping it one way or another to match the tumor?
Yeah, so I think I pointed out when I showed the Bragg peak and the spread out Bragg peak that the Bragg peak itself is actually so sharp that, say if your tumor is fist size, you'd only really be putting dose in the center of it. Like you'd miss the rest. So you do have to have the variation in energy to cover the depth space. But in terms of that shaping transversely, collimating proton beams actively, like with the way that we do with radiotherapy, with like leaf collimators, would be extremely difficult and produce a lot of secondary radiation because they're such high energy, such high rigidity, as we call it, beams. So we don't use active, usually, active sort of multi-leaf collimator-based collimation. But earlier in proton therapy, they did use patient-specific and tumor-specific shaped collimation devices, which was called a bolus, I think. But those slow down your process a lot because for every patient, from every angle that you're treating at, you have to have a specific thing physically machined. And for protons, that's not just 3D printed plastic like you might be able to do in other fields. It's like solid metal. So that's I guess in the 80s when proton therapy was first introduced into clinics, and the 90s when it was first in hospitals, that is how they treat it. But they've very much moved away from that paradigm toward the active spot scanning. It is more accurate as well. You get better outcomes.
Yeah. Well, with the level of flexibility that you have with magnetic fields, you can imagine doing that with magnetic field, right?
So the product of how you shape a beam using a magnetic field is a product of how the beam starts. So the only way you'd actually be able to do that, and I can't see this happening in anything other than a linear accelerator, would be to have a photocathode right at the start and shape a laser pulse transversely, some funky tumor shape, onto the photocathode to generate a beam that has that shape. But then you have to transport that and accelerate it all the way up and get it around to the patient. With a completely linear system, like my system, will definitely ruin that. And then, yeah, I believe people have had the idea. I've not seen much progress on it but there are people who are thinking of doing that more in the sort of laser accelerator space, but whether you can maintain that transverse shape my answer is I doubt it, just because, especially with protons, because they don't radiate, because they're too low energy to give off something like synchrotron radiation. Any perturbation to the bunch will increase your emittance, so increases the temperature effectively of the beam. So any perturbation, anything that is misaligned, anything that is wrong will ruin that distribution, and you've got no way of recovering it. So the magnetic fields can sort of shape in a focusing sense and higher order multipoles, but we wouldn't be able to create a sort of customized shaped beam because just the physics of the conservation of the phase space wouldn't allow you to. Yep. Good question though, you made me think. Thank you.
Hi, thanks for the talk. I was just asking, so for that magnet technology to like focus the beam, is it, just for my own clarification, is it because like, so the beam would be constantly fluctuating in there, is it because you need to like rotate like the phase of like the bunches themselves to like keep them focused, or
which bit did you mean? Sorry, the beamline that I'm designing, or
yeah, or like almost the magnets which are do they constantly change to like focus the?
So my magnets don't change in time at all. They're fixed in time. Usually you have a series of magnets that either bend or focus the beam. They're just linear magnetic fields, so either a constant field, which is a dipole field, or a quadrupole field with 4 poles, which gives you a y equals bx, basically. So linear magnetic field, which increases with radius. So for a single energy beam, you tune that all up. You have a sort of stable optics, and here it is quite equivalent to light optics, where you sort of, you've got your focusing lenses, you've got prisms or whatever else you're using, and you're bending things, and you're sort of effectively tuning that all up for one color, right, or one energy. That's how normal accelerator optics works. The difference in accelerator optics is you can't focus in both planes at once. You can only focus in one plane, and that will defocus a beam in the other plane with a magnet, just technicality. But imagine I've got a red beam coming through. I tune the whole system up with all my lenses, my magnets for that red beam, and then the next color is orange. If I put that orange beam through that system, it literally doesn't reach the other end. Is that kind of what you were asking? So in time, when you're delivering a single energy beam down, all the magnets are fixed in time. The change happens between the energies. So it's not a constantly fluctuating magnetic field. There is a changing magnetic field in the synchrotron that ramps. So you have to ramp up the energy of the magnets in real time as the energy of the beam is accelerated in the synchrotron, just like they do over the radar.
Oh yeah, I was more focused on like how you keep the bunches from how you say, like just hitting like the walls.
Yeah, right. So that's called alternating gradient optics, which provides the focusing. So if I have a focusing quadrupole and a defocusing quadrupole like this, and these have 4 poles, which generates a field which is linear. So magnetic field increases in space. So from here, that magnetic field increases in space. So now I'm looking side on, and I send a beam through here. Any particles which come in here will focus down. Any particles which come in here will focus down that way. So my beam, and this is now in, say, the X plane, In the X-plane, my beam gets focused down there, and then this one is defocusing, so it comes back out again. And if you just repeat that, structure again and again, your beam is stable. Within some limitations. If I do this in the opposite plane, so for the same energy, if I use red to indicate the y dimensions of the beam, then I might be coming in like this in the y dimension. This one would then act as a defocusing, and then this one would act as a focusing quadrupole. And so overall your beam does this. It squishes and, yep. So as you go along the beamline, that's what your beam does. The higher order magnets, say a sextupole where you've got 6 poles, which gives you a quadratic field shape, that's used to correct. So you can imagine here if my beam was slightly the wrong energy, it might do something slightly dodgy like that. That's called chromaticity in accelerator optics terms. And the higher order fields, like the quadratic ones, are designed to account for effects like that. They're not used so much. The ideal accelerator design is usually linear. And then any of these nonlinearities can cause additional complications when you have hundreds of thousands of particles, and it can cause, perturbations that can give you resonances and things like that, which can further make you lose your beam. So it's kind of like, I describe it as like people think about particle beams like they're laser beams. They're really not. It's more like taking galaxy dynamics and translating it down into a microscopic size. It's much more like that. These are beams as well that don't interact with themselves. These are low intensity beams. Once you have high intensity beams, all the particles are physically repelling each other as well, right? Which makes it even harder. Accelerator Physics 101. Thanks for the question.
I was a little bit confused about this moving target problem.
Oh yeah.
Just because, so when you said if you pulse very fast, you can avoid the moving target problem. But if you do that, don't you have to know at which moment in time your target is in where you're going to pulse? Because if you imagine, say, like breathing, if the person has breathed out, the target has moved, you have to make the pulse at the correct time.
Yes.
In that, like, breathing process or whatever, if you imagine it like that, then how do you know at which point in time your target's in the right place?
So you can get that from the imaging data. So you can do, obviously you do pre-imaging, but then you also have a certain amount of online imaging as well with what's called a cone beam CT. So there's a sort of online imaging at the same time that you're treating. It's not as advanced as like your MRI and CT and the full scale one, but it can allow you to sort of have reference points, which can then show you sort of how much movement there is. So the idea, I guess, would be that you would time it so that you're like, okay, well, we know that the least movement happens in this phase of the breathing cycle, and you just be like, right, go, done. That's I mean, obviously, all programmed in, and no one is standing there shouting go. But
yeah. So it like this. There would need to be a software interaction between the imaging system and the pulse.
Yes, and that already exists to a certain extent. Yep, because they've already sort of had to implement that for some of the breathing cycle, but also there are groups working towards 4D CT and 4D MRI, which is where you have that time-based measurement as well. So Paul Keel's group at University of Sydney are quite leading on the 4D imaging. So we have lots of chats about implementing all these things together. Actually, one of the interesting things that we're talking about there and sort of next generation thing is the integration of proton therapy with MRI imaging online. And that's really interesting because a lot of the studies that have been done show that one of the limitations in that is that when you, because MRI magnets are really, really, really sensitive, they're even more precise than our magnets. So if you change the beamline magnetic field upstream, you have to recalibrate your MRI on every step. And that blew my mind because I was like, oh wait, so hang on, if you use my beamline where nothing has to change, your MRI also doesn't need recalibrating, which is a potential huge advantage. So there's lots of directions that I guess we may go in. The question at the moment is, does it work? So hopefully yes is the answer. Thanks for the question.